Let's talk about an element that can help kill stars. And no, I don't mean iron. I'm Sanjana Curtis, and this is Stardust, a series where you and I will do a deep dive into the elements of the periodic table, their astrophysical origin stories, and their role in our lives here on Earth. Today's element is neon. With 10 protons in its atomic nucleus, neon is a noble gas, a member of the famously non-reactive group of elements at the far right of the periodic table. Neon has 3 stable isotopes, neon 20, 21, and 22. All 3 isotopes of neon are made in stars through various nuclear fusion processes. Neon 20, which is the most abundant isotope of neon, is made mainly through carbon burning. After a star has gone through the hydrogen burning phase, where it fuses hydrogen to make helium, and the helium burning phase, where it fuses helium in the core to make carbon, it reaches the carbon burning phase, where it begins to fuse carbon. At the end of the carbon burning phase, the star's core is made of mostly the elements oxygen, magnesium, and neon. If a star is between 8 to 10 times the mass of our Sun, this is where nuclear fusion in the core of that star will stop. Stars in this mass range are not able to create conditions that can fuse elements all the way up to iron. But the star is still not able to avoid an explosive death. It explodes in something called an electron capture supernova. Stars in the 8 to 10 solar mass range end up with cores made of mostly oxygen, neon, and magnesium, supported by pressure due to electrons. When the core becomes dense enough, the magnesium and neon in the core begin to consume these electrons through a reaction called electron capture. These electron capture reactions reduce the pressure from electrons in the core, causing it to collapse, which eventually leads to an explosion. The famous Crab Nebula is thought to be a remnant of an electron capture supernova. Even though there's plenty of neon in the universe, there is not a lot of neon here on Earth. This is because neon is not just reluctant to combine with other elements, it's also highly volatile, so it's hard for rocky planets like the Earth to hold on to neon. Air contains only 0.0018% of neon by volume, which makes its discovery all the more impressive to me. Chemists who were studying the composition of air realized that even after you remove nitrogen and oxygen from air, there remains a small bubble of gases that is unreactive. Neon was one of the elements in this unreactive bubble of noble gases. It was finally discovered in 1898 thanks to the red glow that neon produces when you run an electric current through it. This is the aspect of neon that's most familiar to us thanks to its widespread use in advertising, once people had figured out how eye-catching neon signs could be. A final interesting thing about neon is that there is some terrestrial production of neon going on in the Earth's crust and mantle through naturally occurring nuclear reactions. Specifically, neon 21 can be produced when neutrons and alpha particles produced in the radioactive decay of elements like uranium and thorium combine with nuclei of oxygen or magnesium. This is not any meaningful level of production in terms of the cosmic level of neon, but it does matter here on Earth and has interesting implications for geochemistry. So, for example, for understanding the chemical evolution of the interior of the Earth over time.